Dear student, now we will discuss the remaining parts of the metal oxide semiconductor field effect transistor as a amplifier, as a switch and CMOS. So in this part, we will study about the MOSFET application as a amplifier switching device. So in the saturation region, the MOSFET act as a voltage control current source. Changes in the gate to source voltage VGS gives rise to change in the drain current ID. So thus the saturated MOSFET can be used to implement a transconductance amplifier. Large signal operation of the MOSFET as amplifier. The transistor characteristics, the basic structure of common source amplifier in this figure. So grounded source terminal is common to both the input and output. Here change in V1 or VGS equal to V1 gives rise to change in ID. So we are using a resistor RD to obtain an output voltage V0. So output voltage V0 equal to VDS equal to VDD minus RD ID. In this way, the transconductance amplifier is converted into a voltage amplifier. To determine the voltage transfer characteristics of the CS amplifier, we will assume Vj to be in the range of 0 to VDD, that is the DC biasing voltage across the drain terminal. So here is the basic structure of common source amplifier, that is the transfer characteristics of the amplifier between drain current versus drain to source voltage, in which VGS is the voltage across the gate to source. We take the different voltage of VGS and draw the graph between ID versus VDS. So there are different regions in this transfer characteristics of amplifier. So there is a saturation region and also a triode region, and we draw a load line on the transfer characteristics of this amplifier, and we have the different operating point in this graph. The transfer characteristics of the amplifier, we have VDS equal to VDD minus RD, ID, and straight line on the ID VDS characteristics curve show the ID VDS relationship in this graph. Since VGS equal to V1 for V is less than VT, the transistor will be cut off, ID will be 0, and V0 equal to VDS equal to VDD at the point of A in this graph. So as Vi exceed Vt, the transistor turn on, ID increase and V0 decrease here. This corresponds to points along the segment of the load line from A to B. So A to B is the load line. So in this graph, we have identified a particular point in this region of operation and labeled it by the point Q. It is obtained for VGS equal to VIQ and has the coordinate VOQ equal to VDSQ and IDQ here. So saturation region operation continue until V0 decrease below VT. And at this point, VDS equal to VGS minus VD, and the MOSFET enters a triode regions. So this is the triode region. Point V is defined by the VOB equal to V1V minus VT. For V1 is greater than V1V, the transistor is driven deeper into the triode regions. The characteristics curve in the triode region are bunched together. The output voltage decreases slowly toward zero. Here we have identified a particular operating point C obtained for voltage V1 equal to VDD. The corresponding output voltage V naught C will usually be very small. The large signal operation, the transfer characteristics, so basic structure of common source amplifier in this first figure, and second, so the characteristics of the VI characteristics or transfer characteristics of the MOSFET amplifier. In this graph, point C obtained for V1 equal to VDD, the corresponding output voltage V naught C will usually be very small. This point by point determination of the transfer characteristics result in the transfer curve shown in figure. Observe that we have its three distinct segments here, each corresponding to one of the three regions of operation of the MOSFET. Q1. Now, MOSFET used as a switch. When the MOSFET is used as a switch, it is operated at the extreme points of the transfer curve. The device is turned off by keeping V less than VT. Here, V not equal to VDD. The switch is turned on by the applying a voltage close to VDD. Here, V naught is very small. The common source MOS circuit can be used as logic inverter with the low voltage level close to 0 volt and the high level close to DC voltage VDD. Next, operation as a linear amplifier of the MOSFET. To operate the MOSFET as an amplifier, saturation mode is maintained. The device is biased at the somewhere near to the middle of the transfer curve. The voltage signal to be amplified Vt is then superimposed on the DC voltage V1Q. By keeping Vt sufficiently small to restrict operation to an almost linear segment of the transfer curve, the resulting output voltage signal V naught will be proportional to Vt. That is, the amplifier will be very nearly linear and VQ will have the same waveform as Vt, except that it will be larger by a factor equal to the voltage gain of the amplifier at the operating point Q. So the voltage gain is equal to the slope of the transfer curve at the bias point Q. The slope is negative, hence the bias CS common source amplifier is inverting. If the amplitude of the input signal Vi, the output signal will become distorted since operation will no longer be restricted to an almost linear segment of the transfer curve. So, analytical expression for the transfer characteristics. From the VI relationship, we can see that from this graph, the MOSFET operate in three regions: cutoff region, saturation region, and triode region. So first, the cutoff region. In this region, we have here Vi is less than Vt and V naught equal to Vdd. And next, saturation region. The region segment is AQB. Here Vi is greater than Vt and V naught is greater than Vi minus Vt. So triode region segment VC, here Vi is greater than Vt and V naught less than Vt, Vi minus Vt. Now next is the single stage MOS amplifier. So what is the basic structure of MOS amplifier? In this figure, show the basic circuit to implement the various configuration of discrete circuit MOS amplifiers. Due to effectiveness and simplicity, constant current biasing technique is used for biasing the CMOS transistor. In this figure, indicate the DC current and the DC voltage resulting at various nodes. Characterizing amplifiers in single stage MOS amplifier. The amplifier is with single source having an open circuit voltage V sign and the internal resistance R. These are the parameters of an actual signal source. Similar, RL is an load resistance. Parameters RI, R0, R, ABS, AIS, and GM pertain to the amplifier proper, that is, they do not depend on the value of R and RL. By contrast, R input, R output, AB, AI, GB naught, and GB may depend on one of both R sig and RL. As mentioned above, the non-unilateral amplifier Rn may depend on RL and R output may depend on R sig. No such dependency exists for unilateral amplifier, for which R input equal to Ri and R out equal to R naught. The loading of the amplifier on the signal source is determined by the input resistance R input. The value of R input determines the current that the amplifier draws from the signal source. It also determines the proportional of the signal V signal that appears at the input of the amplifier. In this figure, show an amplifier feed with a signal source having an open circuit voltage V signal and internal resistance R signal. So these can be the parameters of an ideal signal source. The amplifier is shown with a load resistance RL connected to the output terminal in this figure. So here RL can be an actual load resistance of the input resistance of a succeeding amplifier stage in the cascade amplifier. Also in this figure, show the amplifier circuit with the amplifier block replaced by its equivalent circuit model. The input resistance R input represent the loading effect of the amplifier input on the signal source. So R input equal to Vi upon II. R input and R signal form a voltage divider that reduce V signal to the value Vi. So V input equal to R input upon R input plus R signal into V signal. The second parameter in characterizing amplifier performance is the open circuit voltage gain AB naught, defined as the AB naught equal to V naught upon VI when RL equal to infinite. The last parameter is the output resistance R naught from figure. R naught is the resistance seen looking back into the amplifier output terminal with VI set to 0. So R naught equal to Vx upon Ix. As R naught is determined with Vi equal to 0, the value of R naught does not depend on the R signal. So here output voltage V naught equal to RL upon RL plus R naught into A V naught Vi, and voltage gain of the amplifier AB equal to V naught upon Vi equal to AB naught into RL upon RL plus R naught, and overall voltage gain GB equal to V naught upon V signal. So GB equal to R input upon R input plus R signal into AB naught into RL upon RL plus R naught. So this is the overall voltage gain of the single stage MOS amplifier. And also we have input resistance with no load. So Ri equal to Vi upon Ii when Rl equal to infinite, and input resistance R input equal to Vi upon Ii. Open circuit voltage gain A V naught equal to V naught upon Vi when Rl equal to infinite, and voltage gain AB equal to V naught upon Vi, and short circuit current gain AIS equal to I naught upon II, RL being 0, and current gain AI equal to I naught upon II. So in the next short circuit transconductance, so GM equal to I naught upon VI when GL equal to 0, and output resistance of the amplifier proper are not equal to Vx upon Ix. So these are the different parameters, and overall voltage also here GB equal to V naught upon B signals. So in this figure, show a common source amplifier feed with a signal source V signal having a source resistance R signal. Analyze this circuit to determine R input, AB naught and R naught. Here assume RD is part of the amplifier. Thus, if a load resistance RL is connected to the amplifier output, so RL appears in parallel with RD. In such a case, we wish to determine AB and GB as well. So replacing the MOSFET with its hybrid pi model without R naught, we obtain common source amplifier equivalent circuit as shown in second figure. In this figure, and here R input equal to infinite, and V input equal to V signal, VGS equal to VI, and V naught equal to minus GM VGS RD. So AB naught equal to V naught VI equal to minus GM RD, and we have also AB equal to minus GM RD parallel to RL. So GB equal to V naught upon V signal equal to minus GM RD into RL upon RD plus RL. Next one is the MOSFET internal capacitance. So MOSFET have the internal capacitance. So what is the internal capacitance of the MOSFET? In this figure, the various internal capacitance are shown for N-channel MOSFET operating in the saturation region. There are four terminal capacitance. First one is CGS, across the gate to source, and second is the CGD, capacitor across the gate to drain. Result from the gate's capacitance effect, CSB, capacitance across the source to base, and capacitance CDB, across the drain to base are the depletion capacitance of the PN junction formed by the source region and the substrate, and the drain region and the substrate respectively. The polysilicon gate form a parallel plate capacitor with the channel region where oxide layer work as a dielectric as shown in this figure. So gate or oxide capacitance per unit gate area is denoted COX when the channel is tapered and pinched off. The gate capacitance is given by 2 by 3 WL COX. There are two other small capacitance resulting from the overlap of the gate with the source region or source diffusion and the drain region or drain diffusion. Each of these overlaps has a length LOB and thus the resulting overlap capacitance COB are given by COB equal to WLOB COX. Typically, LOB equal to 0.05 to zero point 0.1 L. We can now express the gate to source capacitance CGS as CGS equal to 2 by 3 WL COX plus COV. For the gate to drain capacitance, we note that the channel pinch off at the drain and source CGD to consist entirely of the overlay component C naught B. So CGD equal to C naught V. The depletion layer capacitance of the two reverse bias PN junction formed between each of the source and the drain diffusion and the P-type substrate. Thus, for source diffusion, we have the source body capacitance CSV equal to CSV 0 upon under root 1 plus BSB upon V naught, where CSV 0 is the value of CSV if 0 body source bias and BSB is the magnitude of the reverse bias voltage and V naught is the junction built-in voltage on 6 volt to 0.8 volt. Similar for the drain diffusion, we have the drain body capacitance CdV. So CdV is the drain body capacitance equal to Cb naught upon under root 1 plus VdV upon V naught, where CdV naught is the capacitance value at 0 reverse bias voltage and VdV is the magnitude of this reverse bias voltage. Note that we have assumed that for both junctions, the grading coefficient m equal to 1 by 2. So here is a problem given here different parameters. So calculate the following capacitance when the transistor is operating in saturation. So we find out different parameters by the given or different values. Next, use of MOSFET as a high frequency model. So in high frequency model, equivalent circuit model for the MOSFET as shown in this figure. This figure shows the small signal model of the MOSFET, including the four capacitance CGS, CGD, CSV, and CDV here. This model is used to predict the high frequency response of MOSFET amplifiers. The equivalent circuit for source is connected to the substrate. When the source is connected to the body, the model amplifies considerably as shown in figure. In this model, CGD, although small, play a significant role in determining the high frequency response of amplifier and thus must be kept in the model. In this equivalent circuit model with CDB here neglected, so capstance CDB can usually be neglected here and resulting in significant simplification of manual analysis. The resulting circuit is shown in this figure. So simplified high frequency T model. So figure show the high frequency T model in its simplified form in this figure, and also MOSFET high frequency model summary here. So there are different values of different transconductance and different capacitance of the MOSFET amplifier given here. Next, what is the frequency response of a common source amplifier of a MOSFET? So this is so the frequency response of common source amplifier. So we draw the frequency response between voltage gain versus frequency here and magnitude of the gain of a discrete circuit MOS amplifier versus frequency. So there are different regions in which low frequency band in this frequency response and mid band, all capacitance can be neglected here, and 20 log of A and dB, that is the bandwidth of this frequency response. And here also a high frequency band and a low frequency band and a mid frequency band. Gain falls off due to the effects of coupling and bypass capacitors here, and gain falls off due to internal capacitance effects of the BJT or the MOSFET in the high frequency band region. So FL is the low frequency and FH is the high frequency here. So the difference between FH minus FL is the bandwidth of this frequency response of CS amplifier. So figures show at low frequency, the magnitude of the amplifier gain falls off due to coupling and bypass capacitor. Here it is assumed that their impedance were small enough to act as short circuits. At midband frequency, as the frequency of the input signal is lower, the reactance 1 upon j omega c of each of these capacitors become significant. This results in a decrease in the overall voltage gain of the amplifier. Lower and upper cutoff frequency FL and FH are the frequencies at which the gain drops by 3 dB below its value in midband. Bandwidth equal to FH minus FL and bandwidth equal to FH integrated circuit amplifier and FH minus FL equal to discrete circuit amplifier. So this is the two bandwidth for discrete circuit amplifier and integrated circuit amplifier here. Next topic is the CMOS inverters. So what is the CMOS inverters? The CMOS inverter is constructed by using NMOS and PMOS transistor. So for construction of CMOS, we use the two-type transistor, NMOS and PMOS transistor. And also we can see this CMOS inverter figures in this given here. There is the two transistor NMOS and PMOS here. As the PMOS transistor passes strong 1 and weak 0, it is connected to the supply voltage VDD, and that is the DC supply voltage. Next one is the NMOS transistor. passes strong 0 and weak 1, it is connected to the ground. So NMOS and CMOS passes the opposite uh, values to each other in this CMOS inverter figure. And what is the circuit operation of this given circuit diagram? So we consider the two extreme cases in this circuit diagram. First one, when Vi is the logic 0 level or low level, which is 0 volt. And when Vi is at logic 1 level, which is VDD volt or high level. So there is two cases. One is logic 0 and second one is logic 1 level. In both cases, for each of X position, we shall consider the N-channel device Qn to be the driving transistor and the P-channel device Qp to be the load. And as circuit is symmetric, so this assumption is arbitrary and the reverse would lead to identical result in this circuit operation. So there are also circuit operation of CMOS inverters here. Circuits with when Vi equal to VDD and equivalent circuit of the CMOS inverter in second diagram, where R resistance are DSN equal to 1 upon under root Kn dash W upon L into VDD minus V input. So these are the two different circuit operation diagrams here. And also there is a CMOS inverter transistor transfer characteristics here between output voltage upon input voltage here. So there are different regions in this transfer characteristics also here. And here is also slope +1 and slope -1 also here, and transistor Qn off region and QP also off region, and Vm equal to VDD upon 2, and Qn in saturation region, and also shown here QP is triode region. So there are different regions in this transfer characteristics of the CMOS inverters and represented here. And so there is the reference for this topic, microelectronic circuit by Edel S. Cedra and Kenneth C. Smith, 7th edition of this book. So this is the reference books for this topic. There are some multi-choice questions here also. These questions are very important and very interesting to clear the concept of this topic. So we will discuss these questions one by one. Though, so here the question first, the MOSFET is almost ideal as switching device because metal oxide semiconductor field effect transistor is almost ideal as a switching device because, so option A, it has longer life. Option B, it works progressively. Option C, it consumes low power. Option D, it has linear characteristics. So here the correct answer is the option C, because MOSFET is almost ideal as a switching device because it consumes low power. So in this MOSFET, the power consumption is very low. So due to this reason, we use MOSFET as a switching device in the electronics engineering field, or also application of MOSFET as a switching device. Next question is that IGFET is a device. So this is IGFET is a device. Option A linear device. Option B logarithm device. Option C half power device. And option D square law device. So IGFET is a square law device because it follows the square law in this operation of this IGFET device. So IGFET is the square law device. So correct answer here is option D. In next question, the main type of field effect transistors are main type of FET are option A BJT and FET, option B UJT and FET, option C JFET and MOS FET, option D none of the above. So here the main type of field effect transistor are, so here correct answer is option C JFET and MOS FET, because the field effect transistor have these types. First one is the junction field effect transistor JFET, and second one is the metal oxide semiconductor field effect transistor, and also MOSFET again divided in two parts. First one is E MOSFET and second is D MOSFET also here. So main type of field effect transistors are JFET and MOS FET. So correct answer is option C here. In next question, the MOSFET stand for. What is the MOSFET stand for? Option A metal oxidized selenium FET. Option B metal oxide surface FET. Option C metal oxide semiconductor FET. Option D metal of surface FET. So MOSFET here stand for the correct answer here option C. MOSFET stand for the metal oxide semiconductor field effect transistor. So MOSFET stand for metal oxide semiconductor field effect transistor. So correct answer is option C here. In next, the enhancement metal oxide semiconductor field effect transistor is option A normally of MOSFET, option B useful as a very good constant voltage source, option C widely used because of easy in its fabrication. Option D, normally on MOSFET. So the enhancement metal oxide semiconductor field effect transistor is the option A. Correct answer here, normally for MOSFET, because there are two types of MOSFET. One is the enhancement type MOSFET, and second one is the depletion MOSFET or D MOSFET or E MOSFET also. So correct answer here is option A. In next question, in MOSFET, N channel is more preferred than the P channel because in question say that in metal oxide semiconductor field effect transistor, here the basically MOSFET also two types, N channel MOSFET and P channel MOSFET. What generally N channel MOSFET more preferred as compared to P channel MOSFET. So what is the reason in this case why we use the MOSFET N channel? So what is the reason of this? So option A here, N channel MOSFET, it is a cheaper. The second option for this N MOSFET, it is faster. And option C for N MOSFET, it has better drive capability. And also option D here, it has better noise immunity. So for N MOSFET channel, correct option, it is faster as compared to P channel MOSFET. So the speed of the N channel MOSFET is high as compared to P channel MOSFET. So due to this high speed, N MOSFET channel is more preferred as compared to P channel. In next question, the depletion N channel MOSFET or N MOSFET, option A can be operated as a JFET with zero gate voltage. Option B, N channel MOSFET can be operated as an enhancement MOSFET or E MOSFET by apply positive bias to the gate terminal. Option C, N-channel MOSFET can be operated as an enhancement MOSFET by apply negative bias voltage to the gate terminal. And option D here, N-channel MOSFET cannot be operated as an enhancement MOSFET. So for the N-channel MOSFET, here the correct option is the option B, because the depletion N-channel MOSFET can be operated as a enhancement MOSFET by applying positive bias to gate terminal, because we applied in this case in depletion N-channel MOSFET, we apply the positive biasing voltage to the gate terminal. So here correct answer is the option B. In next question, Metal oxide semiconductor feed effect transistor MOSFET has greatest application in digital circuit due to. So what is the reason for MOSFET? So MOSFET has greatest application in the digital circuit. What is the reason of this? So option first A is low power consumption. It has low power consumption. Option B, it has less noise. Option C, it has a small amount of space. So it takes on a chips. Option D, all of the above, all of the above. So correct answer here for the MOSFET has the greatest application in digital circuit due to the a low power consumption. So we know that the MOSFET is the low power consumption device. So due to the this application or this advantage, the MOSFET is greatest application is the digital circuit. Next question and last, the enhancement and channel MOSFET. Option A cannot be operated as an enhancement MOSFET. Option B can be operated as a JFET with zero gate voltage. Option C can be operated as an enhancement MOSFET by applying negative bias to gate. Option D can be operated as an enhancement MOSFET by applying positive bias to gate. So here correct answer option A, the enhancement and channel MOSFET cannot be operated as an enhancement MOSFET. So thank you very much.